At this point in time, I can't tell how many clusters we have, because then you would do the simple multiplication, you would know how many machines we have, and this is secret. Next, I pointed my binary that I want to run, some command line arguments for this binary, and then comes the interesting section called requirements, which is I'm declaratively specifying how much resources my process will need to run. So in terms of memory, local disk, and CPU. In this case, 100 megs of RAM and disk and 0.1 cores. And the very last line, I want to run 10,000 replicas of this task, which means I want to run this hello world server on 10,000 machines. Okay, so what's happening, Borg will take this binary and will find 10,000 machines in the data center that I pointed it to. This was IC data center, whatever it means. And we'll do it so we'll basically find 10,000 machines such that each machine has at least 100 megabytes of RAM free, 100 megabytes local disk free, and 0.1 core available to be used. So you may ask, okay, but what's the guarantee that these processes will not, actually cheat and spend more resources, like more CPU or more RAM? So for this purpose, we had to introduce a feature in Linux kernel, actually, back like around 10 years ago, which is called control groups. This is a kind of isolation feature in a Linux kernel that lets you define exactly these things. Lets you define that this process cannot go above certain RAM usage or cannot use more CPU than a given number of cores. And this has been contributed to Linux kernel back 10 years ago, and this is like a foundation for actually being able to do bin packing way of scheduling multiple processes on the same physical machine. All right, so the funny thing is that these days the term container. How many of you have heard about containers? Okay, like 30% or more, not bad. So it's getting quite popular, but the funny thing is that these containers, we've been running them for more than 10 years now, just we didn't call it them this way. And actually all applications in Google, like web search, Gmail, YouTube, you name it, everything is run in containers. So we did some calculation to run around 2 billion containers per week. All right, so but going back to Borg, I'll explain real quick how the architecture looks like. So again, cell is a data center. On each machine in the data center, we run a Borglet. So here, a data center consists of 4 machines. Usually, it's as I said, a few thousands. And there is a single Borg master. Actually, not a single because it's replicated for resiliency. But logically, it's a single Borg master with multiple Borglets. And let's see what happens when I was deploying my Hello World application. So first of all, when I'm building my binary, our build system would put it into a distributed storage in a data center that the Borg will later pull this binary from there. And by the way, this build system has been recently open sourced. It's called Bazel, and this is a nice distributed build system. Okay, next thing, the config file is the file that I showed you. The file that was a very simple file that was referencing the data center, the binary name, and the resource requirements. So there is a command line utility called Borg config, which basically uploads this configuration file to the Borg master. Borg master stores it in a replicated persistent store. There's a Paxos algorithm used to make sure that there is a consistency between these replicas. And Next thing that's happening, there's a separate process called scheduler that basically observes what is there in Borg master that has to be done. And in this case, it will figure out that, hey, there is like 10,000 tasks to be run that are not running anywhere yet. So the scheduler will go ahead and find 10,000 machines that have enough resources for this job. And we'll go to every single Borglet and tell it, hey, pull this binary and run it. And this will happen 10,000 times. So what's going to happen, in this data center, there's going to be number of hello world processes executed. And, well, actually being run. So now the question is how many? Like we asked for 10,000, but actually the problem is that with this scale, the failures are getting, important. You cannot ignore them. So you have a slim chance, you have some slim probability that there will be like machine failure, like physical failure. But when you are running on 10,000 machines, the probability that the failure will happen within a week at least once is getting into like a significant numbers. So on this chart, what do we see here? There are two bars: prod for production priority and non-prod for non-production priority. So when you're scheduling jobs in Borg, you can choose whether you're using production or non-production priority. Non-production priority, you can see that you can expect roughly for each single task that you run there, and for instance, we run 10,000 tasks, so for each of these 10,000 tasks, you can expect around, like 8 failures a week. And majority of them would be called by preemption, and preemption happens when a scheduler decides that there is something with higher priority that has to be executed on this machine because there is no other room for this anywhere else. So the lower priority job will be preempted and then maybe rescheduled on some other machine. So basically some kind of defragmentation of resources on this machine will happen. And what it means, your task has to be prepared for this. That is, at any time it can be like rescheduled on a different machine. In production priorities, as you see, there's mostly machine shutdowns. That can go wrong. So these are the things like, hey, we are doing kernel upgrade or something like that. Okay, so the bottom line is, at certain scale, you need to care about the failures, and this is not a big problem. This is like a business as usual. You just need to design your systems to deal well with failures. So we have this allegory: pets versus kettle. So when you run, like when you have a single pet, you usually feed it manually. When it gets sick, you will take it to the doctor and cure it. And this is not what you do with cattle, right? Cattle you just put on the field and they will find the resources, meaning grass in this case, right? And then if one cow gets sick, you pretty much has to kill it. And then maybe some new cow will arrive, will buy it or whatever. So the same, it sounds brutal, but that's how it is, and you have to do the same with your software, which means you have these 10,000 tasks, your kettle, you just want to put it on the cluster, and then each of these can be killed sometimes, and this should be fine for your business. So what it means is that you have to design the application in the right way, of course. So ideally you would have stateless servers, so then at any time the task can be killed, respawned, the same machine, different machine, doesn't matter because it doesn't have any state. So as soon as it's back, it can start serving new requests. If you do have some storage, then ideally you would not obviously, keep it in non-replicated memory, but you would keep it in some replicated storage for resiliency. And the task should be designed in a way that as soon as it's started, it should kind of catch up its state from whatever this storage is, if it has to have a state. So these are kind of basic design principles when you do this, scalable applications and reliable applications. Okay, so we talked a bit about the failures problem at scale. Now we're going to talk a little bit about the utilization problem at scale. So I mentioned that scheduler is doing bin packing to kind of make sure that we are using all resources that we have bought, all our machines. And this is not a trivial problem. This is actually a multi-dimensional problem, because there is not one type of resource. There is, at least in this case, like I just showing two types of resources, like CPU and RAM. So what are these bars? These different. So like a single column across these two charts represent a single physical machine, and then these different colorful bars, basically different tasks or processes that were scheduled on this machine. And ideally, we would have everything packed fully, so we know that we are using all the resources that we bought. This so-called stranded resources is a situation which we are trying to avoid. So in this case, you can look at the CPU, and the CPU is fully utilized, but RAM is not, which means that this RAM is wasted. Nothing will get scheduled here because there is no such processor that needs 0 CPU and some RAM, right? So this is like one of the examples of like a challenging task for this algorithm, and yeah, non-trivial. So this is types of the algorithms that we've been trying to improve over years in Borg. All right, so actually the chart above was showing how we bin pack various tasks on physical machines, and those tasks happen to be virtual machines. So people tend to run multiple virtual machines on physical machine. Now I'm going to talk a little bit about how containers relate to the way people today do deployments in production environments. So virtual machines are super popular. The reason for that is usually you want to run 2 applications at least, or more. Like I showed you that we want to run as many as we can on a single physical machine. In this case, I'm showing the virtual machine, but for the time being, doesn't matter. So if I want to run 2 applications, I run into all sorts of problems. They may depend on different versions of libraries. They may depend on different configurations of operating system, of networking subsystem. And basically, it's not easy to configure them like independently, right? So that's why people actually, this is one of the reasons people do virtualization, right? People would, create multiple virtual machines, run them on the same hypervisor, single physical machine, and then they will have these applications isolated. So they would achieve the same goal that we have achieved with containers, but in a much more heavy way, because each application would be run not in a separate container, but would be run in a separate virtual machine where there is a separate operating system being run, so a separate kernel. And this is kind of redundant. We are basically wasting resources. So the better way would be to cut here and then have containers. And that's what we're doing on Borg. And that's what I believe that containers are good for. One of the things that are good for. They let you run multiple applications on a single physical or virtual machine, doesn't matter in this case, in a single operating system, single kernel environment. And because they are isolated by containers, you have a lot of freedom. How do you, combine them? How which containers are run together on which physical machine? So basically, the bottom line of all of this was that we really learned at Google that we should be thinking about the data center as a single computer rather than a collection of computers. That we have a one application that's maybe a huge application that needs like a few thousand tasks scheduled on multiple computers, but from user perspective, it's just I'm deploying my application to this data center and that's it. And the system takes care of scheduling these tasks on various machines in such a way that they don't disturb each other, these various applications that may end up being run on a single machine, and then we utilize these machines that we buy. So we thought that this is actually a cool idea, and that maybe some other companies in the world may also want to use this kind of paradigm of doing DevOps basically, right? So as soon as you have a big scale, as you have many machines, you want to make sure that you are actually using what you're paying for. This could be physical machines or virtual machines in public clouds you buy in Amazon or Google or Microsoft or whatever, and you still want to make sure that you're using what you're buying. So hence the Kubernetes project. So the Kubernetes project is meant to solve exactly same problems. So DevOps, ease of deployment for large clusters, and optimization of the utilization of your machines. So Kubernetes is an open source project. It's written in Go. So you can contribute if you like Go. It was been really inspired by Borg, and you can run it on bare metal. That means on your own machines, or you can run it in cloud. Actually, Google has a product called Google Container Engine, which is like deploying for your Kubernetes cluster on GCE virtual machines. So you don't have to first buy virtual machines and then set up Kubernetes cluster. Just do one click and you have virtual machines with Kubernetes cluster set up for you. If you want to do it on your physical machines, you have to set up Kubernetes cluster on your own on these machines. So if you want to get started, there is a cool page, kubernetes.io/doc/hello-node, that contains like a nice example of a hello world application. I don't have time to go through this example, this tutorial, but this is a very simple tutorial. What it does, it helps you configure a Kubernetes cluster using Google Container Engine. So it's one click and you have the Kubernetes cluster. And it lets you build, walks you through building a Docker image with a simple Hello World application, and then schedule it to be run on a Kubernetes cluster. I will not get into the details of architecture of Kubernetes clusters. This is going to be very introductory presentation about the concepts that Kubernetes is introducing. But basically, the architecture is very similar to Borg. There is one Kubernetes master, and there are kubelets running on each of the machines in the cluster. And Kubernetes master will be responsible for scheduling your tasks on kubelets. So right now I'm going to go through the kind of key concepts in Kubernetes. So containers, some of you already know what they are. I try to explain. In Kubernetes, Kubernetes has been originally based on Docker containers, and Docker containers basically provide the level of isolation, by using control groups, the stuff that we've been using internally at Google, and also isolating file system namespaces, networking namespaces. Docker containers are also very handy for packaging your applications and then deploying. It's very easy to deploy your container or your image to different environments. The overlay file system lets you do incremental image over the other one. So you can configure, let's say, you can have one Docker image that maybe configures, let's say, your web server environment, and then on top of that have different images that deploy additionally some applications to these web server environments. And these will be really incremental images. So that's what Docker, I think, is good for. So it gives you isolation, gives you ease of packaging and deployments. Okay, that's cool. So Kubernetes is introducing a concept of pod, which is actually combining multiple containers together. And this is actually making this, isolation a little bit less strict. So sometimes you may have some, vertically integrated stacks, like maybe you have a web server that's serving. This is one container. And then maybe you have another application, which is a log saver, which would read the logs from local disk that web server is writing to, and then you want to export these logs to some distributed analytical, huge log processing service. So one needs to write to a disk that the other has to be able to read from. You still want them to be separate containers because they are, logically these are different components. You can have different Docker images with them. But you want to deploy them in such a way that they can share some storage, for instance, so volume in this case. So this is what pods are for. So lets you basically a little bit, get rid of some of these boundaries between containers. In this case, this is really the shared IP address, shared volumes, also some inter-process communication. Okay. The next concept, labels and selectors. Everything you have in Kubernetes, and so far we've learned about containers and pods, can be applied to an arbitrary tag called label. In this case, I have 4 pods, and each pod is assigned 3 labels. One label is defining my application. The second label is defining which environment this particular component is running on, whether it's production or test environment. And then the third label defines which component in my application it is. In this case, I have an application that consists of front-end and back-end. And because I have production and test environment, I have 4 components altogether. And so then I can do SQL-like queries, selectors on these to select maybe all of them, maybe just all front ends, or maybe all back ends, or maybe the production environment, or maybe the test environment. So this is like a handy way to kind of grouping things in Kubernetes and then addressing them. Next concept, replication controllers. Replication controllers lets you define how many copies of the pod you need. So this is like one of the key things that we need. Remember in Borg, we were saying how many replicas do we want. In this case, we're saying by creating a replication controller that, hey, this pod should be run 10,000 times, for instance. And the configuration is declarative, same way as you've seen in Borg. So you just put a number, and then the system takes care about, actually actuating it. That is, making sure that if you say 10,000, there should be 10,000. If there's less, we'll create more. If something was killed, it will recreate one for you. It's like a continuous, control loop that runs in the background that tries to reconcile the state to the one that's intended by the user. And services. Services is once you have multiple pods replicated by a replication controller, you may want to actually expose them to the outside world as one service with load balancer. So this is what services means is created for. So it's again, you very easily declare, hey, this is, you pretty much use selectors to pinpoint like which pods are constituting given service, and then they're assigned a single virtual IP address and this load balancing happening on top of that. So I'm going to real quick go through how Kubernetes is doing networking. Oops. Did I break something? Okay. So if you're familiar with Docker containers, if you run an application inside Docker container, I mentioned that the networking namespace is kind of isolated, so the application may think that it runs on port 80, and you can have another application that's running in a different container, the same physical machine, also thinking that it's running on port 80, but the container port, the internal port inside the container, it gets mapped to a different port of the physical machine, right? Or of the network interface of the physical machine. So what it means is that if you have an application that wants to talk to its replicas across physical machine, it actually doesn't know exactly what port they run on, etc. So you need network address translation, and this gets nasty if you have a big environment in management of these. So the Kubernetes folks decided that this is not enough what Docker is providing, and that we really need a smarter way of doing networking in Kubernetes clusters. And here every pod is actually being assigned its own IP address, and the kubelet is having some subnetwork here. And so the pods that the applications, they are just everywhere, and they may be everywhere on the same port. They know their IP addresses, so they can pretty easily talk to each other, and there is no nuts involved here. So much simpler. Okay, so I'm running out of time. 1 minute. So just like a summary of Kubernetes. So I started with this, presenting you the key challenges that Kubernetes is trying to solve. That is, optimize the utilization of a large number of machines and making it easy to schedule scalable applications on the clusters. But actually Kubernetes is trying to do a little bit more. It's trying to be a single configuration API for the cluster. And the cluster can be either on-prem or in the cloud, right? So with things like services, abstractions like services, you're pretty much telling declaratively like what your application is supposed to do, what services needs to expose, and then all the networking is configured for you, for instance, right? So it's not only scheduling processes, it's actually configuring networking for you, routing rules, everything. Load balancers. And right now the guys are working on adding things like horizontal pod auto-scaling. So when there's like more traffic coming into your service, the Kubernetes will pretty much increase the number of replicas in your replication control automatically. So this is really higher level system than just scheduling processes on machines. When it's in the fullness of time, this could be a single API to configure your whole IT infrastructure that will be independent of where you run it, which cloud provider, or maybe these are your machines. So this is the vision, right, for Kubernetes. And some key design principles is like, I actually started something which is not here, which is like, it should be holistic. It should configure your whole IT environment in a declarative way so that it's easy. And declarative, that means the system runs control loops which make this declarative happen. It's network-centric. For application, it should be pretty much transparent that they are actually running, maybe sharing the same physical machines. And you have to design your stuff as cattle, not as pets. That's pretty much it. The last slide is this is the list of people who contributed to Borg project internally. Many of these are actually working on Kubernetes projects right now. You may encounter a number of Polish names here. That's because like the Borg project and Kubernetes project is run in 2 sites in US and 1 site in Europe, which is Warsaw, Poland. So if you need more advice about Kubernetes, about Borg probably not, then just you can contact me, and then I can kind of get you in touch with people who are actually developing the stuff and are based in Poland, and we're happy to help you. Also, if you want to start contributing. Thank you, and questions.
Давайте поблагодарим докладчика. Вижу.
Thank you very much for your lecture. I have a question. Does Google use only virtual machines, or does it use only physical ones?
We do physical machines, and we do containers on physical machines. So we isolate applications through containers, which is this lightweight weight of isolation, not the heavy weight, which would be the running virtual machines. However, we are selling virtual machines to our customers, which means that we are not. Okay, so let's put it this way: containers are some way of isolating applications, but they are not hacker-proof. right? They are still running on the same kernel. So we are not brave enough to put our customers' code into our data centers, isolating them from our code only by containers. So So basically we need to run virtual machines. And if you want to start code of multiple customers on a single physical machine of ours, we would rather sell virtual machines that tell you, hey, you can run container on our machine. Does it answer? No? Okay.
Well, thanks. I have a couple of questions about pods. Well, the first one is how are containers run in the pods? So are they running on the one physical machine, or they can be distributed?
This is a single machine. It's a single kubelet.
Okay. And one more question is, what are the actual advantages of using pods instead of containers with multiple processes inside?
You can do better isolation between these processes, right? So if you don't believe these processes and you still want to say, hey, you should not spend more than this amount of RAM or this number of CPU cores, then this is what container lets you do, right? So it's basically, it's getting rid of some isolation, like maybe they can start sharing, they can start doing some inter-process communication, but they have some rules.
Ignacy, thank you for your speech. My question is, which kind of containers do you use in production? Docker, Rocket, Linux containers?
So, like you're asking about Kubernetes project or internally at Google? Internally, we have our own stuff, but it's based on the contributions to Linux kernel that I mentioned. So. And our virtual machines that we sell as part of Google Compute Engine the virtualization is based on KVM.
Hey Ignacy, thank you for your speech. So one part that I quite not get is, where does the replication controller run?
Replication controller runs on every kubelet.
Okay, so kubelets. Yeah, and it controls basically the consistent number of pods, right?
I mean, sorry, there is a tool. On every kubelet there is a process that kind of monitors the state, and then there is on Kubernetes master there is a guy who actually orchestrates all of this. Yeah.
Cool. Thanks.
Any questions?
Thank you. Docker is stateless. Where do you put your databases?
So you can use there is a concept of image repositories. So if you're a user of Kubernetes, you can either put stuff in public repository if you like, or if you will, or you can set up your private repository of Docker images. And that's probably the preferred way for majority of users. For us internally, we are using Borg, and Borg has its own. I mentioned this distributed storage of packages, and this is not Docker. This is something built internally before Docker existed, like 10 years ago.